Good morning, learners. My name is Mr. Pochilola. I represent BLACKSLIDES online. Welcome to this lesson. This is a mathematics lesson, Form 3 Mathematics. We are going to explore what are called irrational numbers and surds. If you are watching this video lesson on our YouTube channel, consider subscribing to the channel and hit the notification bell. This will help you to receive notifications every time we upload new material to the channel. If you are learning on our main platform, the learning platform, don't forget to complete the exercises that are linked to this lesson and submit your work in form of a picture to the number shared here. Welcome, learners. Invite your friends to this channel so that they too can be engaged this holiday. Remember, these are holiday lessons which are going to run up to the first week of September. Welcome, learners. Without further ado, let's get down to the business of this time. Welcome, learners. As a starter, can you use your calculator, scientific calculator, to work out these roots? Simply punch on your calculator the square root of 36, the square root of 144, the cube root of 8, and the fourth root of 16. Also go ahead, find the square root of 2 and cube root of 21 using your calculator. What do you find? I'll give you some seconds to complete these roots. Right, so if you have used calculator to find the values of these roots, you find that square root of 36 is 6, and that of 144 is 12. While the cube root of 8, you should be able to find a 2. And the fourth root of 16, you should be able to find 2 as well. While the square root of 2, what's the square root of 2? Should be able to find a value that is approximately equal to 1.41, and the cube root of 21 you should be able to find something close to 2.76. All right, so just have these values on your mind as they are going to make sense as we continue with the lesson. Welcome, learners, to the platform. All right, make sure, I hope you have a calculator that can help you to do this, because that's the essence of the lesson. Because for some of these, it's not that easy without a calculator to find the square root of 2, for example. And it's not easy as well to find the cube root of 21 without a calculator. Make sure you have a calculator, scientific one, just to help you to do some of the calculations that we may encounter in mathematics, physics, chemistry, and the other subjects that need mathematical computation. So in this lesson, still with the values that you found on your mind, in this lesson we are going to discover some important and interesting laws relating to what are called Surds. We shall discover what Surds are shortly. So we are presenting this lesson to you in order to explain what a Surd is and to investigate the rules for Surds. So in the lesson you're going to learn some rules governing to Surds or related to Surds. And we are going to use these rules to simplify Surds. Don't worry, you're going to discover what Surds are. So what is a Surd? S-U-R-D. What is a Surd in mathematics? From the previous starter, you found that the square root of 36 is 6, and that of 144 is 12, and the square root of root 2 is 1.41, whereas the cube root of 21 is 2.76. What do you notice? Among these values, what is your observation? Okay. So these roots, the square root of 36 and square root of 12, 144, have exact values, like 6 for square root of 36 and 12 for square root of 144. These roots are called irrational. They are rational. So numbers whose square root can be found exactly without decimals are called rational numbers. These are rational numbers. Root of 36, root of 144 are rational numbers. Whereas root of 2 and root of 21. You can also think of root of 3, root of 5. These roots cannot be found exactly. So these roots do not have exact values. As you notice, these are not whole number values. You have 1 point something for square root of 2 and 2.76 for square root of cube root of 21. So these roots do not have exact values, and they are called irrational numbers. These are irrational numbers. You can think of other irrational numbers. For example, if you take square root of 3, what do you find? Square root of 5. Can you find square root of 5 when you calculate a square root of 7, square root of 11, square root of 10, etc., etc., square root of 12, square root of different other numbers which don't give you exact values? Those are called irrational numbers. They are also called surds. So in other words, irrational numbers or surds are numbers whose roots are not exact. They're numbers with non-exact values, while as rational numbers are numbers whose roots give exact values. They're called rationals, rational numbers. Irrational numbers are numbers whose roots do not have exact values. By exact values, we mean they don't give you whole number values. They are fraction numbers, values, the values with decimals. And it's hard for some of these values to be calculated mentally unless you are endowed with the mathematical prowess to do so. Your examiners will not ask you to define irrational numbers or surds. They'll simply expect you to apply the knowledge of your understanding of rational and irrational numbers. So think of square root of 25. Square root of 25 gives you 5. That means square root of 25 is rational. Square root of 49 is 7. It is also a rational number. But numbers like square root of 30, square root of 23, square root of 8, all those numbers don't give you exact values, exact whole number values. Therefore, they're called irrational numbers or surds. Let's explore adding and subtracting surds. Adding and subtracting a surd such as root 2. It can be treated in the same way as x variable in algebra. So the following examples will illustrate this point. We have 4 root 2 plus 6 root 2. So you treat these as like terms, like you'd say 4x plus 6x. You can find 4x plus 6x, that's 10x. But now we are not dealing with x here, we are dealing with root 2, which is surds. Root 2 is a surd, implying that you cannot find the exact value of root 2. So to add surds of this nature, 4 root 2 plus 6 root 2, the result is 10 root 2. In the same way, you'd find 4x plus 6x is 10x. So supposing that x here is root 2, so root 2, 4 root 2 plus 6 root 2 is just 10 root 2. You can add these because they are like terms. They are like terms. Like terms can be added very easily. Like you'll say 2y plus 2y, 4y plus 6y is 10y. So supposing that now we are not talking about root 2 instead of y, 4y plus 6y is 10y. So 4 root 2 plus 6 root 2 is 10 root 2. So easy, right? Look at this. We're looking at 16 root 23 minus 7 root 23. These are also like terms. They are like terms in the same way you'd say 16x minus 7x. The result is 9. The result is 9 root 23. These are like terms. The same way you deal with the x variables in the algebra. Now look at this. 10 root 3 plus 7 root 3 minus 4 root 3. You treat these as like terms as well. 10 root 3 plus 7 root 3 is supposed to be 17. 17 minus 4 root 3, what do you find? You find 13 root 3. In case I've left you behind, don't hesitate to send us a text message in the numbers shown. We'll be glad to re-explain what we have not made right in this first place. Welcome, learners, to this channel. Take note that root 2 plus root 3 does not equal to root 5. No. Why? Because these are unlike terms. Root 2 and root 3 are unlike terms. You can't add them up as easily as that. So take good note of this. Let's look at rules of surds. Remember, in mathematics, we have a lot of rules. We have what are called the rules of indices. We have rules of logarithms and other rules. So surds also have rules which you have to know and apply to solve problems. So the first rule is root of a times root of b is just the same as root of a times b. Root a times root b is root ab. In other words, the root of individual, when you multiply the roots of separate terms, that's the same as multiplying the two terms and you put them under a common root sign. For example, root of 6 times root of 4 times root of 6 is the same as root of 24. Just take 4 times 6, that's 24, and then you compute the square root of 24. It's the same. So all we have done here is to multiply the two numbers 4 times 6 and then put them under a common root sign. Another example is root of 4 times root of 10 is the same as root of 40. Just take 4 times 10, that's root of 40. Alright, so I want you to do this for me. Can you list the first 20 square numbers? What are square numbers? Numbers such as 1. The number 1 is 1 times 1. So 1 is a square. Numbers such as 4 is the same as 2 to the power 2. So 4 is a square number. Can you complete the rest of the numbers? I'll give you a few seconds to do that. Alright, so you should be able to find the following numbers. All these numbers are called squares, or square numbers. So you have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. 1 is 1 squared, 4 is same as 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, 36 is 6 squared, 49 is 7 squared, 64 is 8 squared, 81 is 9 squared, and 100 is 10 squared. Shall you see the usefulness of these numbers as we go? How do we simplify square roots? Some square roots can be broken down into a mixture of integer values and surds. So integer values are whole number values. Numbers such as 2, 3, 5, 6, those are integer values. But those that cannot be written down exactly are called surds. So you can have a mixture of some square roots can be broken down into a mixture of integer values and surds. For example, let's look at 12, square root of 12. Trust me, square root of 12 is a surd, because you can't just write down the exact value of square root of 12. If you use a calculator to punch a square root of 12, you find it's going to be 3 point something. But you can write this as a mixture of integer values and surds. So remember that 12 is the same as, to find this root of 12, to simplify root 12, we must split or break down 12 into factors with at least one being a square number. Can you think of the factors of 12 such that one of them is a square number? Okay, you find that 12 is the same as root of 4 times root of 3, because 4 times 3 is 12. So we have split root of 12 as root of 4 times root of 3. So what is root of 4? Can you do root of 4 even without having to use a calculator? You can find root of 4 is just 2. So now simplify the square root. If you simplify the square root, this, find that root of 4 is 2, and then you have a surd, which is root 3. You leave it as it is. So root of 12 therefore is the same as 2 root 3. As easy as that. Alright, this is for you to do. Can you in the same way find root of 45, root of 32, and root of 72? Just a few seconds for you to think about this. All right. You should be able to rewrite root of 45 as root of 9 times root of 5. So what's root of 9? Root of 9 is just 3. Therefore, root 45 is 3 root 5. Written as a mixture of rational number and a surd. What about root 32? Root 32 is just the same as root of 16 times root 2. What's root of 16? Root of 16 is 4. Therefore, root 32 is the same as 4 root 2. What do you think root 72 will be? You will notice that root 72 is the same as root of 4 times 18. Which can be written also as 2. This is square root of 4 is 2. Root 18 is root 9 times root 2. But root 9 is the same as 3. So in this case, the result is the same as 2 times 3 times root 2, which is 6 root 2. Right. What do you think about these problems? You leave a comment in the comment section below, or simply send your comment to the number shared earlier. Welcome, learners. very quickly, can you simplify these square numbers, square roots? What's the square root of 20? You write it here without calculator. What's square root of 27? Square root of 48? Square root of 75? Square root of 4,500? And square root of 3,200. Just fill these brackets. What do you think about this? So following the same rules, you find that the square root of 20 is 4 root 5. First, you simplify root 20 as root 4 times root 5. So root 4 is 2, root 5 is a surd, so you leave it like that. Root 27, you should be able to find 3 root 3. And root 44, you should be able to find 4 root 3. This is root 48, sorry. And root 75, you should be able to get 5 root 3. And the root 4,500 should give you 30 times root 5. While root of 3,200 should give you 40 root 2. So these are quite easy things to do. Welcome, learners. My name is Mr. Pochilola, your teacher on this platform. Remember, it is on this platform where you learn the sciences such as physics, chemistry, biology, agriculture, and mathematics. Right now we have mathematics, Form 3 mathematics, on a topic called irrational numbers and surds. Simplifying surds. Let's have these. Can you compute root 20, root 18, half times half, 1 over root 4 and 1 over root 4. Can you quickly do this? Let's see what you find. The results you obtain are going to help us to move forward. Right, if you do this properly, you should be able to find that root of 20 is 2 root 5, while root of 18, you should be able to find 3 root 2. And multiplying half by half, you should be able to get 1 over 4. What did you find here? 1 over root 4 times 1 over root 4. You should be able to find 1 over 4. What do you notice here? Root 4 times root 4 is just 4 without root. In other words, when you multiply similar roots, you get a value that does not contain a root sign. So in this case, root of 4 times root of 4 is 4. Welcome, learners. Let's look at laws of surds again. So by now you should be able to explain how to rationalize fractional surds. We explain what to rationalize means. You should know that root of a times root of a is equal to a. Root of and repeating the roots of multiplying similar roots gives you a term that does not contain a root sign. So you should be able to rationalize the numerator or the denominator of a fractional surd. That's what we are going to look at next. Let's look at the second rule of surds. Remember the first rule we looked at, the product of root of different numbers will give us the square root of the product of those two numbers. And like when you have similar terms, like here, we have root of a times root of a. The result is just a without a root sign. Put 2 where there's a. Root of 2 times root of 2 is just going to be a 2 without a root. Root of 5 times root of 5 is just a 5 without a root sign. So let's appreciate some examples. Root of 4 multiplied by root of 4 is just a 4 without a root sign. As a matter of fact, applying the first rule, this is the same as root of 16, 4 times 4. So what's root of 16? It's just a 4. Root of 13 times root of 13 is 13 without a root sign. So in order to remove a root sign, just multiply the given term by itself. So in this case, root of 13 times root of 13 is 13. Welcome to rationalizing surds. You may recall from your fraction work that the top line of the fraction is the numerator, this one, and the bottom line is the denominator. So 2 over 3, the 2 is the numerator and the 3 is the denominator. So fractions can contain surds also, or irrational numbers. For example, we have root 2 over 3. So in this case, root 2 is a surd or irrational number. You can also have 5 over 4 root 7, where in this case, root 7 is irrational or a surd. Or you can have something like this, 3 root 2 over root 3 minus root 5. So you can have fractions of this nature in mathematics. Okay, so just have a closer look at this. We have a surd here. This is root 2 over 3. Our surd here is root 7. Well, here the surds are root 2, root 3, and root 5. This is going to help us as we look at what is called rationalizing surds. So if by using certain math techniques we remove the surd from either the top or bottom of the fraction, then we say we are rationalizing the numerator or rationalizing the denominator. So the technique of removing the surd from an expression is called rationalizing. In other words, to make either the numerator or the denominator rational. So that's what we'd love to look at now. But remember the rule that root of a times root of a is just a. So in so doing, we have removed the root, or we have rationalized this thing. So this will help us to rationalize a surd fraction. To rationalize the denominator, simply multiply the top and the bottom of the fraction by the square root you are trying to remove. So 3 root 5. To make this root disappear, we just multiply both the top and the bottom by the same thing, this one. That way we rationalize the denominator, this one. So to rationalize the denominator, simply multiply the top, which is the numerator, and the bottom by the fraction by the square root you are trying to remove. Yeah, like this. So 3 root 5, the goal is to remove this root, this one, to rationalize this denominator, to remove the root. So all you do is multiply this fraction by root 5 over root 5. Don't cancel these two, because that's the temptation many candidates get into. They end up cancelling this. It will take you back to this one. So don't cancel this. So the result is going to be 3 root 5. 5 times root 5 times root 5 is 5 without a root. In so doing, you are said to have rationalized the denominator. So the result is going to be, you must recall that root 5 times root 5, which is this one here, is just a 5 without a root. So the result of rationalizing this is 3 root 5 over 5. Again, these cannot cancel out. For now, they are unlike terms. So to rationalize the denominator, multiply the top and the bottom of the fraction by the square root you are trying to remove. Don't cancel these two, because you go back to this one. So root 5 has given us a 5 without a root sign. So what we've done here is called rationalizing surds or denominator. Let's try another one. Remember, multiply top and bottom by root you are trying to remove. So the root we are trying to remove here is root 7. So to do that, multiply the top number and the bottom number by the root 7, like this. So we multiply the top number by root 7, the bottom number by root 7. So in this case, we shall get 3 root 7 over 2 times 7, because root 7 will give us a 7. Times 2, it will be 14. So you get something like this. So we have root 7 3 root 7 over 2 roots 2 times 7. What's 2 times 7? Should be able to get something like this. So we have 3 root 7 over 14. What we've done here is called rationalizing the denominator. You should be able to do similar problems when given to you. Welcome, learners. Let's consider this one. 10 over 7 root 5. Root 5 cannot be divided into 10. There's a temptation that comes, the candidates display. They end up cancelling this 5 into 10. They think that 5 can go into this 10. No, it's not. These are different terms. Root 5 cannot just cancel into 10. No, cannot go into 10. So we are asked to rationalize this denominator, meaning we should remove this root sign. So to do that, you shall multiply the top number and the bottom number by root 5. Shall have something like this. So 10 root 5 over 7 root 5 times root 5. Take note that we have multiplied both the numerator and the denominator by the same root. So 10 times root 5 is 10 root 5. But root 5 times itself is 5. So times 7 must give us 2 root 5 over 7. Take note that it's possible now, this time, for us to cancel 5 into 10. So 5 into 10 goes 2 times. Therefore, the result is going to be, the result of rationalizing this is going to be 2 root 5 over 7. Welcome, learners. My name is Mr. Pochilola, your teacher. In case I've left you behind, kindly say so in the comment section. Point out the area where you are not sure about this. I'll be glad to rectify what I've not made right in the first place. So, this is for you to do in a few seconds. Rationalize the denominator of the following. 7 root 3. So write down the answer here. What would it be? Very quickly. 4 root 6. 14 over 3 root 10. 4 over 9 root 2. Root 2 root 5 over 7 root 3. 6 root 3, 11 root 2. Alright, so for 7 root 3, we should be able to find something like this. Remember, you multiply the top number and the bottom number by the root, the bottom one. So root 3 times root 3 is 3, and then you have multiplying 7 by root 3 is 7 root 3. So you'll be given this one as the result. 4 root 6 is going to be 2 root 6 over 3. Convince yourself that this is what you obtained by showing the steps that bring you here. 14 root 10 is 7 root 10 over 15. 4 over 9 root 2 is 2 root 2 over 9. And the 2 root 5 over 7 root 3 should give you 2 root 5 root 15 over 21. And 6 root 3 over 11 root 2 should give you 3 root 6 over 11. Welcome, learners. Welcome to what is popularly known as conjugate pairs. Conjugate. We meet conjugates in chemistry also. Conjugate acid-base pairs. We also have conjugates in mathematics. Just as a starter, can you quickly multiply these? Root 3 times root 3. Root 14 times root 14. Can you multiply these two? Root 12 plus 3 and root 12 minus 3. Very quickly, in a few seconds. Well, multiplying root 3 by root 3 should give you 3, as we saw. And multiplying 14 by root 14 by root 14 must give us 14. But what do you get when you multiply root 12 by plus 3 by root 12 minus 3? You should be able to get 12 minus 9. So take note that when you change the sign there, notice that in the first place these are the same. The difference is the signs. So this is minus 3, there's a plus 3 there. So to multiply these two, you simply remove the root sign to give you this one, and then you multiply 3 by 3, that's 9. And then subtract, so we have 12 minus 9, which is 3. Root 12 times root 12. By the way, this is, you make this is what is called the, what do you call this again? This is called the difference of two squares. It will lead to difference of two squares. Root 12 times root 12 is just 12. 3 multiplied by minus 3 is 9. So the result is 12 minus 9, which is 3. Conjugate pairs. Would like to explain how to use the conjugate pairs to rationalize a complex fractional surd. So you should know that root a plus root b multiplied by root a minus root b is just a minus b. Generally, these two expressions are called conjugates. In other words, the conjugate of root a plus root b is root a minus root b. It's the same expression, they just differ on the signs. There's a positive sign here and a negative sign there. These are called the conjugates. So you should be able to use the conjugate pairs to rationalize complex fraction or surds, which we are going to look at shortly. So look at the expression here. Open brackets, root 5 plus 2, close brackets. Open brackets, root 5 minus 2, close brackets. What do you notice? Basically, like I said, these brackets are similar. The difference, however, is the sign. Here we have a plus sign. Over there we have a minus sign. So this is called a conjugate pair. Otherwise, these are called conjugates. So one bracket is the conjugate of the other. They differ. Conjugates differ only on the sign. In that one has plus sign, the other one has minus sign. So the brackets are identical apart from the sign in each bracket. But the brackets are the same. We have root 5 there, root 5 there, we have 2 here, 2 there. The difference between them is one bracket has a minus, the other one has a plus sign. So this looks something like the difference between the difference of two squares, difference of squares. So multiplying out the brackets, we get, multiplying these two brackets here, we shall get root 5 times root 5. Just multiply root 5 times root 5. Minus 2 root 5 plus 2 root 5 minus 4. So take note that these are going to subtract and disappear from the expression. Minus root 5 plus 2 root 5 is 0. This is 0. But root 5 is just a 5. And 2 multiplied by 2 is the 4. So therefore, this gives us 5 minus 4, which is 1. So take note, in order to simplify this, just multiply this. Root 5 by root 5, that's 5. 2 times 2 is 4. And then subtract. As simple as that. So instead of doing this complex calculation here, just remember that to simplify or to multiply out conjugates, you simply take the two roots, multiply them out, and the numbers, the rational numbers, multiply them out also. In this case, 2 times 2, you get 4. So the result is going to be 5 minus 4 minus 1, which is equal to 1. So when the brackets are multiplied out, the sides always cancel out. And we end up seeing that the expression is rational, meaning there's no root sign in the end. Welcome to the third rule of conjugates. So when conjugates multiply out, okay, here the conjugates are root a plus root b multiplied by root a minus root b is just a minus b. In other words, you just you remove the what? You end up removing the roots. as long as the expressions contain different signs. In one bracket you have a positive, in the other we have a minus. Alright, so when you multiply root 7 by, sorry, assuming we have brackets here, so we have brackets here like that. We are multiplying these out. So when you multiply them, multiply root 7 plus root 3 by itself, by its conjugate. So this is the conjugate of that. We know it's a conjugate because this contains a minus sign. Here contains a positive sign. So these are conjugates basically. These two are conjugates. So when you multiply these out, you simply remove the roots and simplify. So this is going to give you a 7. Root 7 by root 7 is 7. Root 3 by root 3 is a 3. The difference between them is a 4. Similarly here, root 11 times root 11 is going to give you an 11. Excuse me. And root 5 times root 5 is 5. The difference between them is 6. Simple as that. You'll be able to apply this as we discuss further conjugates. So rationalize the denominator and the expressions below by multiplying the top and bottom by the appropriate conjugate. So you take the conjugate to rationalize this. In other words, to remove this root sign here, you just multiply the top number and the bottom number by the same thing, by the conjugate. Sorry, not the same, but by its conjugate. So the conjugate of root 5 minus 1 is going to be root 5 plus 1. The conjugate is going to be plus. So in this case, we shall have to multiply the top number, the numerator, by the conjugate of the denominator here, which is root 5 plus 1, multiplying the denominator, this one, by its conjugate, shall remove the root sign. So in this case, we shall have something like this. Notice that root 5 plus root 5 is 0. Minus root 5 plus root 5 is 0. So in the end, you shall have something like this. You don't tamper with the top part there, but the bottom part, you see, we have managed to remove the root sign. So the result is going to be, look at this carefully, that's 5 minus 1, which is 4. This 2 into 4 is going to give us this 2 down here. So the result of rationalizing the denominator from this is root 5 plus 1 over 2. Rationalize the denominator and the expressions below by multiplying the top and bottom by the appropriate conjugate. So the conjugate of root 3 minus 2, root 2, it's the same. You just change the sign, becomes a positive. So the conjugate of this is going to be root 3 plus root 2. So multiplying this out, root 2 multiplied by, root 3 times root 3 is just 3. Root 2 times root 2 is just 2. So end up having something like this. So 3 minus 2 is 1. Therefore, the result is simply going to be 7 multiplied by root of 7 open brackets, root 3 plus root 2 close brackets. So I'd like to leave you now. This is for you to do. Right, so kindly complete this and share with me the solutions. I'll be glad to look at your work again. For the time being, let me go. We meet again later in the next lesson. Bye bye.